Today I will be talking to you about my work, The Invisible Gorilla Effect in Outer Distribution Detection, which was accepted at CVPR 2026. Hello, my name is Harry Anthony and I'm a PhD student at the University of Oxford under the supervision of Professor Konstantinos Kamnistas. My research focus is on improving the reliability of deep neural networks for medical image analysis. So let's begin with an exercise. What I want you to do is count the number of basketball passes between players wearing white t-shirts, while ignoring passes between players in black t-shirts. How many passes did you count? Well, the correct answer is 15. But did you notice the person wearing the gorilla costume? Let's watch the video again. This is a famous experiment in psychology known as the invisible gorilla experiment. The idea behind this experiment is to demonstrate the idea of inattentive blindness, where individuals focus on a primary task and can ignore unexpected stimuli due to a lack of attention. Subsequent studies found that unexpected stimuli are more likely to be seen when they closely resemble the intended target. So for example, because you are asked to focus on the players wearing white t-shirts, you ignore the black gorilla costume. There have been many subsequent studies. For example, they added the gorilla to radiography images, and experienced radiographers weren't able to spot them. So you're probably wondering, what is this got to do with computer vision? Well, the focus of today's talk is on outer distribution detection. So consider the setting. I've got a set of images and corresponding labels, which makes up my training data. I can then train a deep neural network to classify these images. Once my model is trained, it can be applied to unseen images from the same distribution as the training data. And this should give us a reliable diagnosis. However, what happens when I apply my deep neural network to images which are slightly different from my training data? We call these outer distribution data, or OOD data. Well, in this setting, we've got images with unseen ink artifacts that weren't seen during training. We call this a covariate shift because these images have the same classes as the training data, so they can still be benign or malignant, but they have an unseen shift in appearance. When we apply ResNet 18 models on both of these datasets, we see a huge drop in diagnostic accuracy. So on the ID data, we have diagnostic accuracy around 90%, and on OD data, this drops to 74%. So this is a huge drop in the accuracy of the model, and this is a very large hazard because it could impact patient safety if this was deployed in a real clinical setting. So this motivates the design of outer distribution detection methods, which aim to detect OD inputs to the model and then discard these predictions as unreliable. So why is outer distribution detection important in medical image analysis? Well, real-world data is heterogeneous and evolving. In clinical settings, there can be large variety in patient demographics, in acquisition settings, in imaging hardware, etc. This is compounded by the problem that it's difficult to make comprehensive and large training datasets, particularly in medical image settings due to concerns such as patient privacy constraints. This is made even worse by the trend that models often make overconfident mistakes. So the model confidence in its mistake can be high, which can confuse a clinician into whether this is a reliable diagnosis or an unreliable diagnosis. And OOD detection can can enable human-in-the-loop monitoring by flagging when an input is unreliable, as well as fostering trust among clinicians, users, and regulators. And this has been highlighted recently by regulators in America, by the FDA, and the European Union in the EU AI Act, which have both recommended evaluating models on outer distribution inputs. So this is going to be a large consideration for AI safety going forwards. So how do OOD detection methods work? Well, you have your neural network and you have an OOD method. And so your model should give both a diagnosis and a confidence score that it is an ID input. Let's say I could plot on the x-axis my ID confidence score, and on the y-axis a frequency for given images. My confidence score should be able to separate ID from OOD data, such that I can place a threshold and say everything below this threshold is OOD, and so these predictions aren't reliable and should be discarded. We can use metrics such as AUC, which is area under the ROC curve, which is a threshold independent metric, which evaluates how good our confidence score is at separating ID from OOD inputs. So a common finding in OOD detection studies is that OOD detection methods that perform well in detecting one OOD artifact don't necessarily perform well in detecting another, which is another way of saying there's currently no state-of-the-art method which is accepted by the community. However, there is very little understanding of what causes the differences in performance between artifacts. So to this end, we introduce a currently unreported bias in OOD detection, with the hope that by studying this bias, we can create new OOD detection methods which are more robust to different artifact types. Because in clinical settings, there's no way of knowing what unseen artifacts a model will encounter during deployment. So to introduce our bias, I first need to introduce the concept of a model's region of interest, which is the area of an image where the model focuses when diagnosing. So for example, in our skin lesion classifier, the model's region of interest is the skin lesion, where the mean RGB value is shown below. Then for our bias, what we did is we separated our OOD dataset by color. So we had our ink artifacts and a dataset we showed earlier. I'm going to separate it into just the red ink images, just the green ink images, so for purple and black. We can measure the Euclidean RGB distance between the model's region of interest and these artifacts. We can separate it into images which have a similar color to the model's region of interest and dissimilar color to the model's region of interest. What we can then do is apply OOD detection on each of these colors separately. So here are some results here. Here is a method called Mahano-Biscore for 25 seeds for our ResNet 18 primary model, where the y-axis here is showing the OOD detection AUC. And what we find here is the red ink has a much higher AUC than green, purple, and black, so it's much easier to detect. Where here, the three asterisks represent that the p-value is less than 1 times 10 to the minus 3. What I'm showing here on the right, this is the histogram for each of our 25 seeds for the green ink and red ink. And what we then did is we applied a Wilcoxon signed rank test, and we found the p-value was actually less than 10 to the minus 5. And we find this trend for other methods too. So for real MVP, which is a flow-based method, we found the same bias that red ink was much more detectable than green, purple, and black ink. So what we found here is that OOD detection performance appears to improve when the artifact is visually similar to the module's region of interest. And this is analogous to the invisible gorilla effect we saw earlier, where unexpected stimuli were more likely to be seen when they closely resembled the intended target. Hence, we called our bias the invisible gorilla effect. So in the OOD detection community, we tend to put OOD artifacts on the spectrum, where near and far are the extremes. So near OD is very similar to our training distribution, where far OD is significantly different to the training distribution. And the prevailing assumption in the community is that the more similar OD data is to the training data, the harder it is to detect. And this is a line that you'll see many times in the literature for OD detection. However, our findings challenge this assumption. We reveal a bias case where the opposite is true. And this suggests that OD task difficulty is not a simple function of global similarity to the training data, but it depends on what the model attends to and how that interacts with the model's OD detection method. So the contributions of this work are the following. We create benchmarks and conduct a large-scale evaluation of the invisible gorilla effect. We identify trends that we find in the results. We hypothesize the causes of this effect, and we use these insights to design new OD detection methods. So let's move on to the methods and materials. So in our OD detection study, we looked at 40 different OD detection methods, and I'm going to go through the taxonomy of these methods for you now. So the main dividing line between these methods is that either internal methods, which use the outputs or parameters of our primary model, trained for our primary task of interest, for example, our skin lesion classifier, so using the outputs parameters of our model. And the other group is external methods, which is a model trained external to the primary model, and this external model is trained just for OD detecting. So let's look at external methods first. We studied 5 different external methods, which we can separate into different groups. So there's density-based methods, there's classification-based methods, which train a one-class classifier to separate ID from OD. And finally, there's reconstruction-based methods, for example, our diffusion model-based approaches, which aim to reconstruct models, and a higher reconstruction error indicates that the input is OD. Going back to our family tree, we can then look at internal methods here, which we separate into 2 further groups. So we have post-hoc methods and we have ad hoc methods. So post-hoc methods can be applied to pre-trained models, whereas ad hoc methods require altering the training of the primary model or its architecture to incorporate OD awareness in some way and improve OD detection. So we studied 5 ad hoc methods, which are shown here, which we separate into Bayesian neural network approaches. So for example, these can change. Our standard neural network has simple weights, whereas a Bayesian neural network will have a distribution of weights in order to calculate the Bayesian probability from output. We've also got architecture coupled methods, which are going to change the architecture of our DNN to improve OD detection performance. So for example, CIDR here is what we call a hyperspherical prototype network, plots data on this hypersphere you see at the bottom and use distance there as an uncertainty quantification metric. And finally, you have outlier exposure methods, where you specifically give the model outliers, and then you have a loss function where you train the model how to treat outliers when it's given. And going back, we also have the post-hoc methods, which again we separate into 2 further groups. So we've got feature-based methods and confidence-based methods. So let's start with confidence-based methods. These are methods that use the primary model's output layer or penultimate layer for OD detection. So we looked at 13 methods here. One of the most well-known is maximum class probability, which is known as the baseline method. And we also looked at feature-based methods. As shown here, we looked at 17 feature-based methods. For example, the Hal-Nobis score, which I talked about earlier. One thing I haven't brought up yet is that these methods have a lot of hyperparameters. So for our feature-based methods, we have hyperparameter choice of where we apply the method in the network. So I can apply it at an early layer, or I can apply it at a later layer. And we want to study if the effect holds with these different hyperparameter choices. So to summarize, studied 40 different OD detection methods over 3 model architectures and we looked at 3,795 hyperparameter configurations. A question I get a lot is, how do you define OOD? For example, if I make a small change to an ID image, for example, corrupting a single pixel, surely we wouldn't count this as OOD because it's so similar to the trained data. Can we give a theoretical definition of what is OOD and what is ID? Well, many papers have tried, and there's a huge literature on this topic. However, there's no single definition of OOD which is accepted by the community. And we can go through why. So definitions are either criticized as being too restrictive, so saying everything outside the training data is out of distribution, or definitions can be criticized for being too broad, for saying only new classes are out of distribution, for example. For both of these cases, you're either saying we're going to throw away too much, so we're going to discard too many reliable predictions if it's too restrictive, or if it's too broad, you're going to let in a lot of unreliable inputs. Another criticism is that these definitions can be circular. So for example, if you define a metric, and then you define OOD using this metric, and then you use this metric as an OOD detector, it's what we call a circular definition. And finally, definitions can make false assumptions on OOD. So one can be that OOD is only images that a model makes a wrong prediction on. However, this misses that models can make correct predictions for the wrong reasons, and they can do that because of OOD features. And so there's many predictions where a model may get the correct prediction, but it's still an unreliable diagnosis. So OOD is usually defined operationally rather than ontologically, which means that we define by experimental setup rather than first principles. So let's do that now. We operationalize OOD for this study into three groups. Semantic shift, which is a new class not seen in the training data. Real covariance shift, which is data which is the same class with a different appearance. And synthetic covariance shift, which we use synthetic corruptions of the ID data. So starting with semantic shift, we use the MBTech AZ dataset, which is an industrial inspection dataset, which I'm not going to go through today due to time constraints, but please read the paper if you're interested. The next group was real covariance shift, which is where we have the same class and a new appearance. And what we did is we looked at the ISIC dataset. So we manually annotated 31,582 images, and we're going to make these annotations public, so the community can use these annotations in their own experiments. So our model was trained to diagnose between benign and malignant skin lesions. So we just used non-planar images in our training data. We removed all duplicates, and we removed any color artifacts in the training data. So this means rulers, ink, and color charts were removed. We used 25 random seeds, and we used 5 five-fold splits. Once our model was trained, we could first look at explainable AI methods, which are methods that aim to show what the model is focusing on when making a diagnosis. So we have 7 explainable AI methods shown here. And by looking at this, we can confirm that the lesion is the model's region of interest in its dataset, which is shown by these 2 examples here. Once the model was trained, we then tested it using OOD artifacts. So we manually annotated 11,355 images, again using a human manual annotator, where we have ink artifacts and color artifacts. We then separated these into colors, which were similar to the model's region of interest and dissimilar to the model's region of interest. So for our ink artifacts, we've got red as our similar, green, purple, and black as our dissimilar. And for the color charts, we've got red, orange, and yellow as our similar, and blue, green, black, and grey as our dissimilar. The question is, how did we define similarity? Well, we had to operationalize similarity. We did this by segmenting the artifacts using SAM2 and human clicks and human quality checks to ensure the masks were appropriate. Using these masks, we can then calculate the mean RGB of a skin lesion, along with the mean color of our similar artifacts and our dissimilar artifacts. We then used the Euclidean RGB distance as our measure of similarity. So you'll see here the similar color artifacts have smaller L2 distances, where the dissimilar have larger L2 distances. The question is, why do you use RGB Euclidean distance? Because there are other metrics that may be similar to how humans perceive color than this metric. Well, we want to emphasize that DNN's process color similarity within its input representation, which is defined in RGB space. And so by measuring RGB Euclidean distance, this enables a more direct measure of similarity in the space in which the network operates. Another step to rule out dataset bias was using the masks that we calculated earlier. We created dissimilar counterfactuals. So we turned our similar, which is our red, yellow, and orange color charts, into black color charts. And we did the same with our dissimilar data. We turned that into similar colors, so the same color as the skin lesion. And then we redid our tests to ensure that the invisible gorilla effect was not an artifact of dataset bias. The final group is synthetic covariate shifts, which I'm going to go through later. So let's go over the results from our large-scale empirical evaluation. So we have feature-based methods we're going to look at first, where the red dot represents the AUC for our similar to the model's region of interest datasets. So that's shown here. And now I can plot the AUC for the dissimilar artifacts. And this is all for a ResNet 18 primary model. What we see is large drops in the AUC between similar and dissimilar artifacts across the 17 methods, but by different amounts. So, for example, negative aware norm in the middle has a huge drop, over 20%, whereas other methods are dropping much less. So, for example, NUSA, as we can see, drops much less. Now I can do the same for our confidence-based methods, which are applied on our penultimate layer of the model. What we see is much smaller drops in the confidence-based methods than in the feature-based methods. Now I can do the same for our ad hoc methods. So I'm here, and again we're seeing large drops across these methods. And finally, our external methods, we're seeing large drops for some methods. For others, such as our reconstruction-based methods, we're actually seeing an inverse trend for the diffusion models. Now I can do the same for our color chart experiments. So again, I'm plotting the feature-based methods. We can see significant drops across the feature-based methods. For our confidence-based methods, we're seeing smaller drops. And then we see drops in AUC for the ad hoc methods too, and same for our external methods. And if you're interested, we have further results from our paper, which shows the same trends hold for the color swap counterfactuals, for different model architectures, such as VITs and BTGs, and for other metrics. So let's do an in-depth analysis of these results. On this plot, on the y-axis, I am plotting the OOD AUC, so the similar artifacts across our real benchmarks. And on the y-axis, I'm showing the drop in OOD AUC between our similar and dissimilar artifacts. And what this plot is showing is there's a weak positive correlation between the best performing methods and a drop in performance, which sort of makes sense because better performing methods have more room to drop because we've got a higher AUC. So another consideration is the balance between OOD generalization and OOD detection. So someone may say, why do we need to detect more visually similar OOD? Won't model accuracy be higher on them? Well, the finding in many OOD detection studies is that model generalization does not correlate with OOD detection. Let me show you what I mean by this. So looking at our ink annotation examples, we find that purple has the lowest diagnostic accuracy compared to black, compared to green. So the model performs best at detecting malignant and benign skin lesions on the green ink OD compared to the purple OD. However, looking at OD detection results from a Hanover score, we see that green is actually the most detectable, then purple, then black, breaking the correlation. This is problematic because in this case, more problematic cases where the model is incorrect are less detectable, which is what we call silent failures. So therefore we want to detect both similar and dissimilar OD. As mentioned before, we studied a large amount of hyperparameters. For example, if a feature-based method can be applied in an early layer or a later layer in the network. But why did we do this? Well, let's plot the hyperparameter results for the Hanover score for red ink and black ink, where the y-axis here represents the model of the ResNet. So what we find is that although red has a higher AUC than black across all layers, I piloted two hyperparameter choices, A, where red and black are clearly separable, and B, where the AUC between red and black is almost the same. We plot this to highlight that hyperparameter cherry picking can change if the effect is shown in the data, and we recommend for any authors to do large hyperparameter sweeps to ensure that the effect is clearly studied. As looking at this hyperparameter sweep, red consistently has a higher AUC than black, but the choice of hyperparameter can change your interpretation of the data. Let's now look at the impact of the model's region of interest on the effect. So one unanswered question is, how does the model's region of interest impact the invisible gorilla effect? Well, going back to our OD datasets, you can look at our synthetic covariance shift data. Remember, these don't reflect realistic deployment conditions, but they're useful diagnostic tools. And we had two different training datasets that we used. Both are CheckSpurt, which is a chest X-ray dataset. So the first training dataset was normal X-ray images, where we train a classifier to diagnose between images with cardiomegaly, which is an enlarged heart, or without cardiomegaly. In the second training dataset, we used synthetic data, where we segmented the heart using check-mask segmentations, and we then reduced the intensity of the heart in the images, so that now a heart appears hyper-intense or dark in the image. Once the synthetic data was made, we then renormalized the dataset and then trained the DNNs on the same task of diagnosing cardiomegaly. So let's look at the results. Here's our hyper-intense heart, so the real data. Once the model was trained, our OD data was we took an ID image and we added a synthetic square, which took up 1% of the pixel area of the whole image, as shown here. We then calculated the OD detection AUC and detecting the synthetic OD. What we then did is we then varied the artifact intensity in the image. So if we make the square brighter in the images, we see that it becomes more detectable. And similarly, we made the square less intense, and we measured the AUC for different intensities. Looking at the results on the bottom left here, you see that there's an asymmetry in the OD detection AUC. And in fact, there's a drop of 6% between when the artifact value is plus or minus 3. A reminder, these images are normalized. So what we found is for the hyperintense model ROI, we found that hyperintense artifacts are more detectable. Now let's look at the results for the synthetic data with our hypointense heart. And we now see that that asymmetry is flipped. So now hypointense artifacts are more detectable. This illustrates an example of the invisible gorilla effect, where detection performance depends on the visual similarity to the model's region of interest. We can now look at the hypothesized causes of the invisible gorilla effect. So we saw in the data that feature-based methods had the largest drop in performance. But why is that? Well, to understand, first I'm going to go through one of the feature-based methods, which is Mahalanobis score. So for Mahalanobis score, I've got an input image and I have my DNN here. What I'm then going to do is use a feature extractor to collect the heat maps at some point in this model. And then I'm going to calculate the mean of these heat maps to get a feature vector, which is Z here. I can then plot Z here, where I can show where the training data may lie, where the ID test data and OOD test data may lie in the latent space. We can calculate the distance of the test data from the mean of the training data using Euclidean distance here. However, what we see is it's unable to separate the ID and OOD data. So a better technique is to take into account the covariance between dimensions in the latent space. So that's what Mahalanobis does here. And it does this by using the covariance matrix calculated from the training data. And if there's multiple classes in the data, what we do is we calculate the mean and covariance for each class in the training data. Then when given a new test input, we can measure the Mahalanobis distance to each class centroid. And we can use the minimum Mahalanobis distance as our scoring function. So now we can introduce our hypothesized mechanism. We hypothesize that color variation in the OOD data aligns with high variance directions in the primary model's latent space. And as many feature-based methods downweigh high variance directions, for example, Mahalanobis, as we showed before, this may mean that color shifts that project onto high variance directions may be underpenalized, which may be causing highly dissimilar artifacts to be harder to detect than more similar ones. How can we test this hypothesis? Well, we can do something called PCA, Principal Component Analysis. PCA analysis works by calculating principal components, where in our equation here, F is the PCA coefficients, V is orthogonal vectors, which are corresponding variances, which is what we call eigenvalues. To test this hypothesis that color variation aligns with high variance directions in the primary model's latent space, we first do PCA analysis on the training data. So we calculate our eigenvectors and our eigenvalues. We then project similar and dissimilar features onto these principal components. We can then compute the ability to discriminate between the similar and dissimilar OD using AEC, so using our projections. And we calculate the 1- as well in case it is a negative correlation. And we use this in a metric we call I. And we use this to define a metric shown here, which is a measure of the OD color sensitivity. And finally, we measure if I correlates with the high variance directions in the model's latent space. So let's look at the results here. On the y-axis, we have our OD color sensitivity. And on the x-axis here, we have the logarithm of the PCA variance. So these are the eigenvalues. What we find is the Spearman rank correlation is 0.47. So there's a positive correlation between the two. And we find that the p-value is 1.5 times 10 to the minus 4. This suggests that there is a positive correlation between the color sensitivity and the variance of the direction in the model's latent space. Finally, we look at mitigation strategies for the invisible gorilla effect. So using a hypothesized mechanism, we define the nuisance latent space, which we define as a span of the 5 principal components with the highest I value, where we have an ablation of different K values shown in our supplementary material. What we do is we project features orthogonal to the nuisance subspace, and then we apply the feature-based methods again with a nuisance subspace taken out. The idea being that once these subspaces are taken out, the OOD detection performance should improve for the dissimilar artifacts. The other mitigation strategy we looked at was color jitter augmentation. We applied augmentations to the training data. we used Torch Vision's color jitter augmentation, which changes the brightness, contrast, and saturation. And we evaluated it at 2 intensity levels, so light augmentation and a heavier augmentation. One thing to note with this strategy is that the classification accuracy of our primary model for our task of interest, so this is the skin lesion data, drops with more extreme augmentations. So for our heavy augmentations, we see that the accuracy actually drops by 5.5%, which is not necessarily what we want for our model. So let's plot some of the results for the color jitter augmentation first. So here is a confidence-based method, virtual logic matching, for no color jitter. I then show the performance for light augmentation and a heavier augmentation. What we find is that the invisible gorilla effect flips. However, the AUCs drop, and the absolute difference between similar and dissimilar actually increases. So although we have flips the effect, this actually makes the system less reliable, and this is not really the outcome we want. Summarizing across all the methods then, so for the confidence-based methods, for color jitter augmentations, we find that the absolute difference between similar and dissimilar actually increases for 12 out of the 13 for light augmentations, and 11 out of the 13 for heavier augmentations. Similarly, we find the AUC for similar drops for all methods for the light augmentations and heavy augmentations. Hence, for confidence-based methods, color jitter augmentation does not improve the reliability of the models. Now going on to feature-based methods, we find that the absolute difference between similar and dissimilar is more mixed. So 6 out of 7 for light augmentations and 4 out of 17 for heavy augmentations. We can plot all the different feature-based methods on the x-axis here, and on the y-axis we can plot the difference in similar and dissimilar AUC. I can now add the light color augmentations and the heavy color augmentations shown here. What we find is that the results were mixed. Classification accuracy dropped for these color augmentations, and the bias grew and shrank inconsistently for feature-based methods. And we did find that the bias flips for confidence-based methods, but this was mainly due to drops in the similar AUC, which is not improving the reliability of the model. Now looking at the other mitigation strategy, nuisance subspace protection. So we first calculate the nuisance subspace on color charts, and then we applied the projection on the ink artifact. So here are the results, first for feature norm, where the red here shows the AUC with projection. So what we find is the bias shrinks for most methods, while maintaining the AUC for the similar artifacts. The only exception here is OOD, where we did see a drop in the similar artifacts. However, we must note that this nuisance subspace projection can be applied on less methods than our color jitter approach. One concern with the nuisance subspace projection is we're going to increase the inference latency. So we plotted here the latency on our ResNet for the method and the method with the projection. However, putting this into context, the inference latency is still much smaller than other approaches, such as our diffusion model approach shown here. So in reality, this concern is not a major concern for the application of this approach. In conclusion, we introduced the invisible gorilla effect, which is a bias where OOD detection performance improves when they are visually similar to the model's region of interest. We created benchmarks and conducted a large-scale evaluation across 7 benchmarks which were made public, 3 model architectures, 40 OOD detection methods, 3,750 hyperparameters, 25 random seeds, as well as color-swapped counterfactuals to rule out dataset bias. We identified trends in the results, finding that feature-based methods had the largest drop, finding the bias can flip by augmenting the model's ROI in training, finding that it does not correlate with model generalization, and finding that the bias can be minimized by hyperparameter cherry picking. We hypothesized causes of the effect, finding that OD color-sensitive directions correlated with high variance directions, and we found that many feature-based methods downweighed these directions, which may be a cause of this effect. And finally, we analysed mitigation strategies, finding that color jitter augmentations showed mixed improvements, whereas nuisance subspace projection was more consistent but can be applied on less methods. And we hope this finding will inspire future work. For example, do these trends hold in other similarity axes, such as shape and texture? And do they hold for other modalities? What about language modelling, and what about multimodal settings? Well, thank you very much for listening. Please follow me on social media, and if you have any questions, please do let me know. Many thanks.